This is the second part where we are speaking about functions as relations. In the second part, we give some examples of infinite functions. But before that, let's look at the definition again of a function. A function f is a relation from a to b which satisfies for me two conditions. First, the domain of f is a. We know that the domain of any relation is a subset of a. So to prove that the domain of f is a, what we need is to prove that for any x belongs to a, x is in the domain. The second condition says that if the pair x and y is in the relation f and xz is the relation f, that means y is equal to z. This is an if and then statement. So to prove it, we need to assume that x and y and x and z is in f. Then we show that y is equal to z. These two methods we needed to use when my relation is infinite. So for our first example, we take a relation G, which all pairs A and B says that the second, which is B, plus twice the first, which is A, minus 7 equal to 0. And this relation is from the natural numbers to the set of integers. I want to show that this relation G is a function. From our discussion from the first slides, since the relation is from n, I need to prove that for any a belongs to n, a is in the domain of G. This is the first things we have to show. And the second thing, we take two elements. We take any two elements x, y, and x, z. We assume these two elements are in the relation G. And we have to show that this y is equal to z. For the solutions, we take a in a natural number. Then from the definition, I said b is equal to minus 2a plus 7. This element, since a is a natural number, this b will be an integer. And so ab belongs to the relation. And this can be verified. For any a with this value b, we have b plus 2a minus 7 will be, the definition of b is minus 2a plus 7 plus 2a minus 7, which will give me 0. That means this pairs is in G, and so a belongs to the domain of G, and so we can conclude that the domain of G is equal to n. So the first condition is satisfied. For the second condition, we assume that the pair an and bm are in my relation G. Then by definition, a and n belongs to G. That means the second, which is n, plus 2a minus 7 is equal to 0, which gives me that n is equal to minus 2a plus 7. And also we have m plus 2a minus 7 is equal to 0. That means m is equal to minus 2a plus 7. And hence we have m is equal to n. And this satisfies me the second condition. So from 1 and 2, we conclude that the relation G defined by this formula is a function from the set of natural number to the set of integers. Now note that since G is a function, we can write that G is a function from the natural numbers to the set of integers, and is given by b is equal to G of a, where G of a is defined by this formula, minus 2a plus 7, which means also that for any a, we can find the only b by using this formula. These are notations which are common in calculus. Let's take another example. Here we have a relation f defined by all pairs x, y. says that the first square plus 4 the second square is equal to 16. The question is to show that this relation f is a function from the interval from 0 to 4 to the interval from 0 to infinity. Now, before we see that this relation f actually satisfies for me the condition from being a function, we see that if f is a relation, this means 4y squared have to be equal to 16 minus x squared, and that means y is supposed to be the square root, plus or minus the square root of 16 minus x squared over 4. This equation here, it is very important for me in the proof, which gives me a way for any x to find a y such that x and y in the relation. For the solution, since f is a relation from 0 to 4, so for the first condition, I will assume x is an interval from 0 to 4. Note that means x squared is less than or equal to 16. So if we set y equal to the square root of 16 minus x squared over 4, this y is well defined since x squared is less than 16. And that means y belongs to the interval from 0 to infinity. And actually, for this x, when we take y to be this value, then x squared plus 4y squared will be equal to, after substitution, it will be equal to 16. That means xy is in f, in my relation f, and so this gives me the domain of my relation f is the interval from 0 to 4. It is very important that when I will take my x in the what is supposed to be the domain, I have to verify that y is in the codomain. Okay, so for any x, I have to verify that y is in the codomain, because if it is not in the codomain, that means I cannot say that x and y is in f. Now we've verified the first condition. Let's go to the second condition. Now we take two pairs and we assume they are in the relation f. So we'll assume that we have a pair t and z in the relation f, and another pair with the same first coordinate t, but a possible second coordinates, and here is w, in the relation f. Now, using the definition of this relation f, the first one, it means that t squared plus 4z squared is equal to 16, and the second bears here in f, it means that t squared plus 4w squared is also equal to 16. These two values here are equal. With the cancellations, it will give me z squared is equal to w squared. But z squared equal to w squared, it means what? It means that z is equal to plus or minus w. But z and w are non-negative. They are in the interval from 0 to infinity. That means there is no change of sign. Both of them have to be positive. That means z is equal to w. This means the second condition is satisfied. We take z and w and we assume they can be different, and we get z is equal to w. In the second proof here, it is crucial to know that the definition of the codomains play parts. Because z squared is equal to w squared, it doesn't mean z equal to w. It means z is equal to plus or minus w. But since both of them are non-negative, this will give me that z equal to w. So we conclude that from satisfying the condition 1 and 2, we conclude that f is a function, and f will be a function from the intervals 0, 4 to 0 infinity. So since it is a function, we can write this we can use this notation. So f is a function from the interval 0 4 until 0 infinity, and we can write it as any element y can be found as a function of x, and this will be given by the square root of 16 minus x squared over 4. And as I said before, this notation are the common notations used in calculus. In the last slide, we discussed this relation f, and we show that it is a function from this interval to this interval. I want to discuss with you another point of view why this f is a function, which helps me to deep understanding why we define functions as relations. So consider the relation f as a relation on the set of real numbers. Then the graph of f is an ellipse crossing the x-axis in -4 and 4 and the y-axis in the point 2 and -2. So the graph of function is this ellipse. However, for this example here, we take f only from 0 to 4. That means we select from this ellipse all the point x, where x is take a value from 0 to 4. And this means what? This means it gives me these 2 points. So when x is from 0 to 4, we get this, this part of the ellipse. But now also we select what is the codomain. The codomain is the values of y which are non-negative. That means we select the values of y which is from 0 to infinity, and this means we are taking only this part of the ellipse. So the relation f, which is from 0 to 4 to 0 to infinity, is this portion of the ellipse, which is given by the equation y is equal to the square root of 16 minus x squared over 4, and this is the definition of my function. Now, this discussion is very important for the next slides, where we give infinite relations which are not functions.